records on this computer. It's always misleading. Good afternoon, everyone. My name is A.Molenda, and I would like to make a short presentation, short lecture from the chiral properties of graphene. And it's always a hard task to keep the attention on site and online, but I will try to do my best to keep your interest. So the way in which I, okay, here it is. The way in which I plan my lecture is going to be a half lecture about research, half of the resume. So I divided the lecture into the introduction, then I'm going to talk about the chiral decomposition of multi-layer system of graphene HBN, that is hexagonal boron nitride. Then I'm going to move into the Klein tunneling, and then I'm going to sum up the lecture. So the main motivation for my research were those two papers you can see on the screen. And in both of these papers, they were described the devices with the use of HBN and the graphene in multi-layer system. And in the second paper, it was pointed out that some of the structure can have usefulness as an intralayer tunneling fed devices. So this was the main motivation for my research. And before I even start talking about research, I would like to introduce the term of chirality because, okay, thank you. Because usually when we think about the chirality, and the topic of my presentation is the chirality in systems, we have in mind some optical property of, especially of the chemical substances. We learned this in school about the reflection of the substances. But in this case, of course, I'm not going to talk about this property, but by chirality, I mean the proper quantum operator. In fact, it's quite abstract operator, and it's connected with some transformation of the Poincare groups. However, fortunately, I don't have to speak about Poincare groups, or maybe unfortunately, I don't know, because in the case of the massless particles, the chirality is equal to another operator, which is called helicity, and the helicity is much simpler, not that abstract. It's just the projection of the spin to the direction of momentum of the particle. And if you ever will be fancy to go through the literature, there is another meaning of the term chirality. Usually in the literature, you will meet chirality as a number of the bilayers that can be divided from the system in some procedure of decomposition, about which I'm going to talk later. Just to avoid the mess, I wanted to at first to tell you something about in which meaning I will use the word chirality in my work. So it may be a bit obvious. I'm dealing with graphene. It's a marvelous material, and it has really outstanding properties, the chemical properties, the physical properties. It's a honeycomb structure with two sublattices denoted on this picture with the letter A and B and the color red and color blue. But what I'm interested more are the properties of the graphene as a laboratory, as a tester for the quantum field theory. As you can see right here on the right side of the slide, there is a picture with the dispersion dependency energy dependent on the momentum, and close to the vertices of lattice, it's a linear energy, a linear dependency, and it can be seen in the equation, since if we are going to write the Hamiltonian in more general way, it's going on the left side, is going to consist of the operators of creation and annihilation. But if we are going to go and do some approximation about it, we are going to do the nearest neighbor approximation and approximate it to the low energy of electrons, or in general, carrier of charge. We are going to obtain a simple Hamiltonian, which is similar to the Dirac wave Hamiltonian. And the Dirac wave Hamiltonian describes the massless particles. It's a Dirac, in fact, it is the Dirac equation for the massless particles. And it's good because we can treat the carriers of charge or electrons in graphene as a massless particles. and they have the maximum speed at the low energy, the maximum velocity at the low energy, the Fermi velocity. And it also happens that due to that similarity of the mathematical form of the Dirac-Weil equation and the Hamiltonian of graphene with some approximation, we also expect that some phenomenon from quantum field theory can be observed in real devices in the physical material in graphene. And another material I used in my research was hexagonal boron nitride. And it is very good material to be combined with graphene, since the lattice, the constant of the lattice constant of HBN is similar to the lattice constants of graphene. There is a difference of 2% in both lattice constant, not that much. And it's also a honeycomb structure. The Hamiltonian of HBN looks a little bit different because we don't have the zero in diagonals. We have the energy coming from two different atoms, the atom of nitrogen and atom of boron, so it cannot be that simplified to the Dirac-Weil equation. Okay, and we can have two geometries, and we are going to focus on ABA geometry because as it was described, and as it was discovered, that only the ABA geometry allows us to make a procedure of chiral decomposition. So just to show you two different geometries, as you may notice, the energy bands are different. And if we are going to explicitly write the Hamiltonian form of both, they are a little bit different too. In the case of the ABA, the coupling between two double layers, just to short remark, it is the Hamiltonian of 4 layers of graphene. So we have 2 double layers, and the coupling of those 2 double layers in the case of ABA, and denoted here by gamma 1, are closer to each other in the case of the ABA and are further away from each other in case of ABC. You can see also already the difference in the energy bands in both cases. So everything's for now sits together. The energy bands difference and the Hamiltonian difference, that's how it should be. And as I said before, we are going to focus from right now onto the ABA structures. And the chiral decomposition of graphene system was introduced in 2008 by Nakamura and Hirasawa. And they noticed that any Hamiltonian can be transformed by some mathematical transformation to the certain effective Hamiltonian, which are inside of this Hamiltonian. And the condition for this transformation, of course, is a conservation of the eigenvalues, because we don't want to manipulate the system. We just want to make some transformation which doesn't change the energy of the system to make it look more friendly for the scientist. So and I will show in the second what is this transformation, how exactly it looks like. It just to tell you that something for right now, it just to tell you that this transformation exists. And if we have the even number of layers of graphene, we obtain n divided by 2 effective graphene double layers. And in the case of the decomposition of the system, which have an odd number of layers, we obtain n-1 divided by 2 effective graphene double layers and 1 single layer of graphene. So just to show you what's happening inside in this Hamiltonian, it is the case of 3 layers of graphene. And as you may see, this on the left upper, it's how it looks like before the transformation, and on the right down corner is how it looks like after the transformation. As you can see, the couplings between the monolayer and the double layer is changed into some effective gamma 1 effective inside of this double layer, which, let's say, absorb or amortizate the lack of this coupling gamma 1. And here we have 0. Oops. Okay, and here we have 0. So that's how this transformation looks like for a very simple case. And one more time, I would like to stress that this transformation is a purely mathematical operation, which then allows us to take this bilayer or monolayer of graphene and operate it as a separate system, but doesn't change the energy, the eigenvalues of this Hamiltonian. Okay, so first aim for my research was creating the procedure for chiral decomposition of multi-layers graphene on a single layer of hexagonal boron nitride. So we use theoretically a hexagonal boron nitride as a kind of the substrate. And here this decomposition looks a little bit different since we, as before, we obtained some effective couplings in the graphene double layers, which amortize the lack of couplings between the monolayer of HBN and the double layer of graphene. But also, as you can see, the energy are modified on the diagonal inside of the double layer of graphene. What's more, there is a modification also of the nitrogen energy inside of the Hamiltonian. And if we have the even numbers of graphene layers, we obtain n divided by 2 graphene double layers and a single layer of HBN. In the case of the odd number of graphene multilayers, we obtain n-1 divided by 2 graphene double layers and graphene monolayer connected with the hexagonal boron nitride. And you can see the characteristic for the bilayers consisting of graphene and hexagonal boron nitride. We can see the characteristic band, which is opening in the case of the monolayer graphene on the right side on the chart. And this chart on the right side is just a magnification of the chart of the left side. Due to the scale, it's easier to observe this change if we take a look, if we zoom into that part of our chart. As you can see, with the colors, with the blue, there are changes inside of the double layer of graphene. With the green, there are changes in between double layer of graphene and monolayer of graphene on the hexagonal boron nitride. And on the right, there are the changes which we observe in this double layer graphene hexagonal boron nitride. And the second aim of the research was investigation how monolayer of hexagonal boron nitride in between the graphene layers can modify electron properties of the system. So before, we only put the graphene on HBN. Right now, we put the graphene, we put the HBN in between the graphene layers. And of course, we have the different cases there on the both sides of the HBN, the number of the graphene layers can be even or can be odd or can be even or odd. All the cases I'm going to show you all the cases with the different number of layers. And if we have even number of graphene, then HBN, then odd number of layers of graphene are reversed. They decompose into n-1 divided by 2 bilayer graphene and monolayer connected with HBN monolayer. And in the case of the decomposition in multilayers, which have even numbers of graphene layers, they decompose into n divided by 2 bilayers graphene and monolayer of HBN. And interesting result is when we have one odd number and the second odd number of the graphene layers, since they decompose into n-2 divided by 2 bilayer graphene, one monolayer graphene which is connected with HBN, but as you can see already from the band, there is a linear dispersion. There's dispersion in the energy band. That means there is one freestanding monolayer of graphene inside. That means that if we adjust a different number of graphene layers and put inside the HBN correctly in a good way, we can modify the system that itself, it has a one monolayer of graphene freestanding and it has the properties of the normal monolayer of graphene. That means all the effects which we can observe theoretically in the graphene and are coming from the quantum field theory also are going to be observed in this graphene inside of the system. And the third aim of my research is investigation of behavior of graphene system with HBM layers stuck inside on HBM monolayer, since we need some substrate for our graphene with HBM inside. It cannot just float in the air. So let's say we put as a substrate an HBM at the bottom of the system. And here we don't obtain the freestanding monolayer graphene. We obtain n-1 divided by 2 bilayer graphene and 2 monolayer graphene connected with the HBM, but we can see that the difference of the band gap is very different in both cases, because in one case it's very small, and in another case it's much bigger. So we can somehow adjust, by the good geometry of the system, adjust the wideness of the band gap in the case of multi-layer system consisting of HBM, graphene, and then HBM. Okay, and the fourth aim of the research was investigation of the Klein tunneling in multi-layer graphene hexagonal boron nitride. And why the Klein tunneling is observed? First of all, the Klein tunneling is the phenomenon which is observed in the quantum field theory for some energy of the barrier, which is 2 times the rest energy of the mass of the particle. We can suddenly see the full transmission of the particle coming to the barrier, and this is called Klein tunneling or Klein paradox. And we have to remind ourselves to see how the Klein tunneling is possible in monolayer graphene. We can remind ourselves about the beginning of the lecture and about the operator of helicity. And if we also we remember how the Hamiltonian looks like, we'll see that the operator of helicity and the operator of Hamiltonian commute together. So that means the helicity is the conserved with the time operator. It doesn't change. The value of helicity doesn't change, which already gives us some intuition that if the particle is going vertically to the barrier of the some height, there will be no reflection, since the operator of helicity cannot change. And moreover, if we look at the velocity of the particle, which is given by the second commutator of the state, the velocity of particle is equal to the operator sigma, which in our case, the operator sigma in our case is responsible for the in graphene for the pseudospin. And it's an equivalent of the spin degree of freedom in Dirac-Weil equations. And if we are going to calculate how the velocity on the x-axis change over the time, we'll see that on the x-axis it depends on the y momentum. And if the particle is going to the barrier vertically, there is no reason for the y momentum or momentum on the y-axis to be changed. That's why also the velocity, it doesn't change if the particle goes vertically to the barrier. And that's why at the zero angle, we obtain the full transmission. This is, that was a little bit of short of mathematical introduction into why the Klein tunneling is happening in this case. Moreover, on this slide, I show you the form of the wave equation. And from more physical perspective, this transmission is just putting the electron, which is in the conduct mass, is shifted through the barrier of potential to the valence bands, leaving then empty states in the conduct bands. That is an equivalent of the anti-states in the Dirac equations. And here is the form of the wave equation. Just to make a short remark, all the coefficients are present inside of the barrier. So in fact, that's true. In barrier, we have the anti-state, that is the empty states in the conduct bands, and the state in the valence bands. And of course, the solution for tunneling is just to joining the equations, comparison equations in the free regions, the wave equations in the free region. That's how we obtain the transmission coefficient. And as you can see, this is the result from Kuznetsov and Novoselov from 2006, and it is the transmission for the Klein tunneling. As you can see, there is a maximum at zero angle, as it should be, but also what appears for some widens of the barrier, as we will see in a second, is the maximum for the transmission coefficient and at not zero angle. And that's because for some widens of the barrier, the potential works as a interferometer. So there is some interference of the waves inside that creates another peak of the maximum transmission. It's the device which we can compare it to. It's a Fabry-Perot interferometer. So for some widens of the barrier, it acts as a Fabry-Perot interferometer. And as you can see, it's really connected with the width of the barrier. So for 80 nanometers, we don't obtain such a tunneling. For 100 nanometers, we obtain this another peak of the tunneling. And also we compared how it looks like for a different coefficient of energy of coming particle towards the energy of the barrier. And in the case of the bilayer graphene, the Klein tunneling was observed, and it was also the same paper by Kuznetsov and Novoselov from 2006. But what Kuznetsov and Novoselov did, they approximate the bilayer Hamiltonian of the graphene into two-dimensional form with 4 elements of matrices. They just shrinked the original barrier, the original Hamiltonian, into the smaller form. We are trying to describe the tunneling with the full form of this Hamiltonian. As you may see, the energy in both cases are a little bit different. The approach we did in our work is a 4-band approach. The approach that Kuznetsov and Novoselov did, it's a 2-band approach. And as you can see, we obtained the 4-band and of the energetic band, and Kuznetsov and Novoselov obtained 2 bands of energy. Of course, what looks different are also the relation of the square of the momentum depending on the energy. In the case of 2-band approach, bilayer graphene, we have the linear dependency, and in our case, it's not linear anymore. And what is similar in both approaches? The similar are the quality of the tunneling. The difference is the quantity, because we obtain 4 maximum for tunneling, while in the 2-band approach there are only 2 maximum of tunneling in this case. So the quality is the same, the quantity is different in both approximation. And as you may see, there is no tunneling at the 0 angle. So maybe we shouldn't call it Klein tunneling. And in fact, in literature, it's called, in the papers, it's called Klein tunneling, but the more proper name for it, it's anti-Klein tunneling. It's also the phenomenon which is observed for the particles with the Hall spin, which is observed in quantum field theory. So as you can see, for the different parameters, we obtain different shapes, different amounts of the peaks. Peaks which denote the maximum of the transmission. And here are also the charts which tells us how it looks like when we compare it with the energy divided by the height of the barrier. It also changes. And just to sum up, I propose and describe a procedure of decomposition following system: multi-layers graphene on substrate from HBM. Hybrid multi-layers consisting of graphene and HBM. I investigated how HBM can modify the structure of graphene multi-layers. And in these special cases, when we have the HBM between 2 odds number of layers of graphene, we obtained the free layer of graphene. We observed the free layer of graphene. I also investigated and described Klein tunneling and used it a little bit as a measure to check if the effective B layers or effective monolayers are really B layers and monolayers. Thank you for your attention.
All right, thank you. Thank you for the presentation. So do we have any questions to the speaker? Yeah, maybe some Zoom audience has some questions. Maybe I will ask this graphene problem. So you come across existence of, so how you relate graphene to superconductivity? Do you have any kind of clue?
In this case, how we relate the graphene to superconductivity?
Yeah, because I see there is like in superconductors you have electrons and holes, and the Hamiltonian structure is very similar to that.
It's
so
very similar.
Like you have Bogusław equations, for example, right? So can you make any comment on that?
To be honest, I don't have the prepared question right now.
Yeah.
Do this. I would have to. I never strictly connected in the mathematical form the Hamiltonian of the graphene, but it's very nice way to be research, of course. When I was doing this research, I was mainly thinking about the transistors because, as you can see, in the Klein tunneling of the bilayer graphene, there are separated transmission. There are separated.
Okay.
Yeah. There are separated peaks, and they are quite sharp. It's not the normal distribution. It's a Lorentz-Breitner distribution. If you look, it's similar to Lorentz-Breitner distribution in this case, and they are separate for the different angle. So maybe in projection of the electronic devices, it can be useful to have this separation because for some angles we can see the full transmission, 100% of the transmission. And there is question for me, how would the Hamiltonian change for integrant speed particles of or excitation, and how this could contribute to the tunneling signal you can be observed. Okay, I think there will be some additional couplings in the case of the integer speed particles, but also just to bear in mind that the tunneling, the anti-Klein tunneling, is similar to the tunneling for the whole integer spin particles excitations. And to be honest, this research was also followed, and there is also paper I found in from 2023, which says that which gives us more realistic, let's say, approach to it, experimental approach. And the Klein tunneling is observed, but for the different shapes of the barrier. So not always this simplest barrier in the theory, this rectangular barrier, can make the best results for the ab initio calculations and experimental methods.
Well, this question about tunneling of particles with integer spin is also somehow related to Josephson junction problem, right? So we have two superconductors. There's the tunneling of particles with quasi-bosons with integer spin. All right. So do we have any other questions? Maybe, but there is more on the Zoom. If you can go up to see. How would the Hamiltonian change if, okay.
I just answered this question, and I mentioned the paper because this work was followed up by some by scientists. Thank you. I will send it by scientists, and they also made a more realistic approach, more experimental, realistic in that way, more experimental approach.
I see.
Or I don't know if you can say more experimental, just experimental approach to this theoretical comparison. So I will send it, of course. I will send the reference for it.
Do we have any more questions from the audience? Well, maybe I will make one comment. Graphene is excellent material for research. It's more like 40,000 or 50,000 papers already published on graphene. The problem is there is no really one single emerging technology from graphene.
Yes.
And big companies like Samsung and many others, if you talk, okay, officially they admit graphene is prosperous material, blah, 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 blah. But no reliable technology was constructed. So essentially, it's still very inspiring material to make a research, but still, I would say that from the point of view of, because if you want to build reliable electronics, you need a high level of repetition, and this is a problem. This is a problem. And some people used to say that the problem of graphene is lack of band gap. That's actually the problem. So they try to introduce band gap artificially.
Mm-hmm.
That's but still you have like quantum Hall effect in room temperature in graphene and many other fascinating phenomena that can be observed. Right. So do we have more questions? If there are no more questions, let's thank the speaker. The last speaker, well, it's time for my talk, but let's say in 8 minutes.
Okay.
So guys, see you in 8 minutes.
Okay. So.